Okay, so we are discussing one-way ranging versus two-way ranging. We noted that in one-way ranging, we also need to estimate an additional receiver clock error term, because of which we need one more transmitter. On the other hand, in two-way ranging, since we are using the same clock to report both times and taking the difference between the times, any clock error or deviation that occurs during the travel time of the signal gets almost cancelled out. The remaining error can be modeled in psi. Therefore, in two-way ranging, we do not require any additional transmitter to determine the clock error. Now, in this case, since the receiver needs to know the time of transmission of the signal from the satellite, and it also requires multiple satellites, it is important that all the satellite clocks are synchronized to a common reference time. So time synchronization of satellite clocks is also very important in one-way ranging. Okay, if the clocks are not synchronized, then that will introduce additional error, and it is highly sensitive because any small error will be magnified by the speed of light. Therefore, in GNSS, the clocks are monitored and also corrected. Okay, and clock errors are transmitted in that information is transmitted in the signal. Whereas in the conventional design of DME, such synchronization is not required, because here we do not form the pseudo range, the range measurement the same way. Then let me see. Okay, so now you may ask then what are the disadvantages of this approach, this two-way ranging? First of all, to get interrogation signal from the aircraft needs to be within the service radius of the base station, which is few hundred kilometers. Okay, so only when the aircraft is within the service radius of a base station, DME base station, it can receive interrogation pulses from the aircraft. The aircraft can also receive return pulse pairs, reply pulse pairs from the base station. Now, this approach, sending interrogation signal to satellites which are far away, is not practically possible. Okay. Another problem with this two-way ranging is that the base station will receive interrogation pulses and wait for some time, and then only it will send back reply pulse pair to the user. Because of this approach, it can serve only a limited number of users over a period of time. So it cannot serve as many users as possible. On the other hand, if the transmitter continuously transmits signals, and whenever the receiver receives the signal from at least minimum number of transmitters, it can determine its position. So that way, it is not required that it has to begin transmission. It does not need to wait for any interrogation for the user. So it can serve any number of users within its service volume. And depending on the constellation design, the service volume can be global or local. That we will discuss later. So in the one-way ranging approach, we can serve as many users as possible. Whereas in two-way ranging, the base station can only serve a limited number of users. That's an important disadvantage. Because of which DME and few more other reasons are also there. DME is undergoing modernization currently. Okay. And as part of modernization, two types of ranging methods have been proposed, both one-way and two-way. Okay, so the conventional approach will be retained, but in addition to that, they are also introducing one-way ranging signals. So in the conventional approach, the aircraft can send interrogation pulses. The station will return the reply pulse that will be retained. In addition to this, for some particular time interval, the base station will stop responding to interrogations and it will send passive, continuously transmit signals like satellites. So whichever aircraft can receive the signal will be able to use it. Okay, so as part of modernization efforts, DME will operate in both one-way and two-way ranging. Way. Okay, nothing else. But to operate in passive mode or in one-way ranging mode, the clocks, the base station clocks need to be synchronized. Okay, like GNSS, the clock should be synchronized. And the advantage of this is that through the signal in the modernization, the signals will transmit additional information like base station coordinates and few other things also it can transmit, which the aircraft can receive, and with the help of additional information, positioning accuracy can be improved. Okay. Any question after this? Okay. The next, yes. Any question?
No, ma'am.
The next method by which we can determine range, not exactly range, we actually determine range difference, is called time difference of arrival, okay, TDOA. An example of this is long range navigation, LORAN. Okay, LORAN is used in aircraft as well as in ships. Okay. Here the approach is different. Okay, and instead of getting range measurements, we actually are interested in range difference measurements in case of LORAN. Again, in the conventional design, LORAN is also undergoing modernization, and they are adopting an approach similar to GNSS. That design is called enhanced LORAN because it is more robust and more accurate. But we are not going to discuss the principles of enhanced LORAN here. We will just briefly talk about the conventional design, which is called CLORAN. Okay, now few things are common to both the things that we actually regarding the system. Whatever I'll tell you will be the same in the similar in the enhanced design also. But the way position is determined in the enhanced version is different. That is similar to GNSS. Okay, since you have already discussed GNSS, I am not going to get into that. And LORAN is also beyond the scope of this class, so I will not get into that. I will just stick to conventional design, which is different from the approach taken by GNSS. In case of LORAN, the entire geographic area is divided into a number of chains. Okay. Now each chain comprises a master transmitter and 2 to 3 secondary transmitters. Okay. So now they are actually operating as a group. Okay. In earlier approaches, we had individual transmitters. They were not interacting with each other. They were operating individually. But now we have a group of transmitters where one is master and the others are followers or secondary transmitters. Now within a group, first the master transmits a number of pulses. Okay. And once the master transmission is over, the secondary transmitters take turns to transmit their pulses one at a time. But there is a fixed time difference between the master transmission and the secondary transmission, and it is different for different secondary transmitters. Now this fixed time delay is known. Okay, the nominal value is pre-calculated and known. It's called nominal emission delay. Okay, so it is known to the user. Once the user identifies the chain, he will know the nominal emission delay between the master and a secondary. Okay. Now, how the user can identify a chain? Each chain has a unique repetition interval, group repetition interval. This is the interval at which the group transmission repeats. In other words, it is the time between two successive master transmissions. So first the master transmits, then all the secondary transmitters transmit one at a time. Once all the secondary transmitters have transmitted, the master transmits again. So the time interval between two successive master transmissions is basically the group repetition interval. So using this time, so each chain has a unique GRI. Okay, and using this, so once the by processing the signals, when the aircraft ship identifies the GRI, it will be able to know which chain it is. Okay. So first the user receives signals from the master. So once it receives the signal, it can, using a clock, it can find the time of arrival or the master signal. Similarly, it will also receive signals from the secondary transmitters, and it can report the time of arrivals of the secondary. So let's consider one master secondary pair. Okay, so let's denote A is the master transmitter, and then B, C, D are secondary transmitters. So TRA here is the reception time from the master, time of the signal from the master. So this is calculated or determined by the receiver, load and receiver on board the user vehicle. Okay, now in the conventional design, the time of transmission of the signal is not known. So at what time the signal started from the transmitter is not known to the user. So to determine the range, we need both the times, right? Time of reception as well as time of transmission. But in this case, the time of transmission is not known. So we cannot form the range measurement like here. We need to do something different. So we get time of reception for the master signal. Then we also know the time of reception from a secondary transmitter. So the range to the master transmitter would be TRA minus its time of transmission. Similarly, range to that secondary transmitter would be TRB minus its time of transmission. Now, if we take the difference between these two range measurements, assuming we could measure, then what do we have? We have TRA minus TRB, and then we also have the difference between the two times of transmission, right? Now, the nominal value of this transmission time difference is known, right? The nominal emission delay is known, right? So now we do not need to handle individual time of transmission. Rather, we are considering the difference, and that the nominal value of the difference is known. So in the conventional design, the transmitters are not synchronized that way. So the actual difference may vary somewhat from the nominal value, and that variation can be modeled in epsilon. But definitely it degrades positioning accuracy. But it can be statistically modeled in epsilon. So this is measured by the receiver. This is also measured by the receiver, and this is known a priori. The nominal value is known. So we can determine the range difference here, right? So for each master secondary pair, we get a range difference. So here the measurement is not range exactly, it is range difference. And since you are considering time differences, so difference between two times of arrival, this technique is called time difference of arrival. Okay. Now we know that the line of position, the lines of position in case of constant range measurement are circles. Yesterday I told you that using DME we do not get good height accuracy. So DMEs are used to determine the 2D position. Similarly for LODAN also we get actually 2D position. So here we are going to see the lines of position, not surface of position. And the measured quantity here is range difference, right? So can you tell me what will be the line of position for a constant range difference? So we know that it is a circle for constant range. But how about constant range difference? What do you think it will be? Did you understand the question? Are you following or not following? If you are not following, tell me clearly. Which part you did not follow?
Ma'am, is it hyperbola?
You are asking me or you are answering the question?
I'm answering.
So you are sure that it will be hyperbola?
I think so.
How about others?
Yes, ma'am. It's hyperbola.
Yes, it is hyperbola. So here we have a master and then 3 secondaries. Okay, so you just take the master and a secondary. So this is a master secondary pair. Connect them with a straight line, and then you basically for constant range difference measurements you get all the hyperbolas. So you just pick any of these, and then for any position of the user, the range difference between the two transmitters will be constant. The transmitters are at the foci. Okay, so this is as per the equation, the basic property of hyperbola. So for one master secondary pair, we get a set of hyperbolas. Similarly, for another pair, we'll get another sets of hyperbolas, right? Now, how do we determine the position of the user? So again, we need to look for the points of intersections of the hyperbolas. And the two hyperbolas can intersect at more than one point. Again, there is an ambiguity. So in that case, we need another pair to resolve that ambiguity. Now, since here we have hyperbolic lines of position, this is also called hyperbolic position. So TDOA, time difference of arrival, is also called hyperbolic positioning technique. Okay. So graphically, we understand how we get the positions from the measurements. Mathematically, what we need to do, for example, here, R is written as follows. So we get to know TT from the signal. After processing signal, we use a clock to determine TR. So C into TR minus TT. This way actually we get the measurement. But then we also need to write the mathematical models of the measurement. So this will be clear when little more clear when I give you an overview of GNSS for the project. So we need to form the mathematical models of the range measurements, and then we need to stack all the measurements that we get from all the transmitters, and then use a filter to determine the positions. It's like solving a number of equations to find the position, but it has to be handled in a different way because there are errors, and that's why we need filters. Okay, so our objective is to remove this epsilon term as much as possible and estimate the unknowns. Okay, so it's equivalent to solving equations to get the unknowns, but the extra thing that we need to do is to remove epsilon as much as possible. Okay, that's all about ranging. If you have any question, we can discuss that. Otherwise, I'll move on to the next technique.
Excuse me, ma'am.
Yes.
Ma'am, how we ensure that this time difference is accurate? Because yesterday you said a millisecond difference can create 1,000 kilometers of error.
Which one you are asking about?
Ma'am, time of arrival, time difference, TR minus TT. How we
And
ensure accurate value?
you are?
How we ensure that this value is correct?
What is your name?
Ma'am, I'm Krishna Kumar.
Krishna. Okay, Krishna.
Yes, ma'am.
So how we ensure that this difference is accurate?
Accurate means
This is
uh, close close value, precise value. I mean.
that's what I said, right? TT we are actually deriving from the signal. So TT is stamped by the clock on the satellite. Satellites have highly accurate atomic clocks, but still the clocks drift. Okay.
Okay.
Now there is a control segment which monitors all the satellites in the constellation. So it is the responsibility of the control segment to make sure that all the satellite clocks are synchronized to a common reference time, that is called GNSS system time. So GPS has its own system time, INSS or NAVIC has its own system time. So each constellation has its own system time, and again it is the responsibility of the control segment to make sure that there is an accurate system time, and at the same time all the satellite clocks are synchronized to this system time. Any deviation has to be uploaded to the satellite and broadcast by the satellite. The user gets that deviation. Any small error that still remains is broadcast in the signals, okay, and corrected by the user when it processes the signal. So we are not much worried about TT. We can determine TT with very good accuracy. That is not the case with TR. TR is reported by an inexpensive user clock, receiver clock. So this will have error. We cannot avoid it, and that's why we have this delta TU term, right? So TR, so basically the reported time will be the true time plus some error, the clock error, which is delta TU. Now I have taken delta TU outside. Now this is true time. So what is reported is basically TR, the true receive time, plus this delta TU, right? Now this delta TU has to be estimated. This is an additional unknown. So we need one more transmitter. This is why in case of passive ranging or one-way ranging, we need an additional transmitter to estimate this receiver clock error. There is an upside also. What is that? Using an inexpensive clock, once you estimate this delta TU, you are basically synchronizing that inexpensive clock to GNSS system time, which is highly accurate. So by suitably designing the receiver, you can use it as a timekeeping device. In fact, that is done. And that's how we derive time using GNSS. Okay? And we can achieve this with the help of an relatively inexpensive clock.
Okay, ma'am. Thank you, ma'am.
Any other question? The next technique that we are going to discuss is angular positioning. As the name suggests, here we are going to make angular measurements. Okay. First, we'll see how angular positioning can be done in 2D, 2 dimension. Okay. Then we'll extend it to 3D. Okay. Now, what are the angular measurements we make? We make 2 angular measurements for 3D, bearing and elevation. In case of 2D, we make only one measurement called for a transmitter, given transmitter, only one measurement is made, it's bearing. So let's first discuss the 2D positioning and then we'll extend this to 3D. So how do we define bearing? Now let's consider this figure to define bearing. Bearing is basically the angle within the horizontal plane. Okay, so we are considering 2D, so everything is in the horizontal plane between a reference and the line joining the transmitter and the user. So if you take this as the reference direction, and this is the line that connects the transmitter with the receiver. So we take this line, and then bearing is basically the angle calculated in clockwise direction from this reference direction to the line connecting the transmitter and the user. It is positive clockwise. Okay, and the straight line connecting the transmitter and the user is called line of sight, LOS. Okay, so along this line we can see or the user can see the transmitter, and that's why we call it line of sight. Okay. Now, in this case, the reference direction is picked at the transmitter. So this is one transmitter, this is another transmitter. So for this transmitter, this is the bearing, and for this one, this is the bearing. So psi 1 and psi 2, always calculated clockwise. Now we can also have the reference direction at the chosen at the user, which is shown here. So in this case, for this transmitter, this is the bearing psi 1, and for this transmitter TR2, this is the bearing psi 2. Okay. Now an example of this is design where the reference directions are chosen at the transmitters is VOR, very high frequency omnidirectional radio range. VORs were used in aircraft in the last century, I mean commercial aircraft. But as we discussed, we'll see that with angular positioning, we do not get good accuracy when the distance between transmitter and user increases. So accuracy degrades as the distance between the user and transmitter increases. So the accuracy with VOR was not so good. Now, after GNSS came into being, with the help of GNSS, DME and LORAN, much better accuracy was achieved. That's why for civil aircraft, VORs are being decommissioned now. For military aircraft, it is still there because by suitable design they improve the accuracy and the corresponding. So basically, they use both DME and VOR a system which has both DME and viewer, and they name it differently. It's called TACAN. Okay. TACAN stands for Tactical Area Navigation. Okay, so they actually use DME as well as VR. They have a different design, much more accurate design, but it is equivalent to DME plus VR. Okay, now an example of this method is camera. Okay, basically positioning with camera is angular positioning. Okay, so yeah, using reflected signals from environmental features, images of the features are developed on the camera detector. Okay, and from the coordinates of these images, what the camera does is it determines both bearing and elevation of the features with respect to the camera frame. Okay, and then it does necessary processing to determine the position. So camera is an example of angular positioning system where the reference is taken as at the user. Okay. So here we see only bearing because we are considering 2D positioning. Now for a given bearing measurement, what will be the line of position? It's basically a straight line. So you just take this line, anywhere on this line we get the same bearing measurement. So in case of bearing, constant bearing, the line of position is a straight line. Now we know that two straight lines intersect only at one point, so there is no ambiguity here. So with the help of two transmitters, we can uniquely determine the user position. There is no ambiguity here. Whereas in case of ranging, if we do not have any prior information, we need a minimum of 3 transmitters, assuming there is no clock error, a minimum of 3 transmitters in 2 dimensions, right? So bearings to 2 transmitters will give user position. Now I need to write the equations and see how. So for this purpose, you can consider this configuration where the reference is taken at the user, okay, and assume that the transmitter coordinates are known, okay, and use an XY coordinate frame. So transmitter coordinates in that XY frame are known, okay. So you need to write the equations. Assume that the user has made 2 bearing measurements, psi 1 and psi 2. So psi 1 and psi 2 are measured by the user. Transmitter coordinates in the frame, XY coordinate frame are known. Write the equations and find the user position. Assume that the reference direction is along the y-axis. So assume that the reference direction is known for this case. Is the question clear to you? What do you have to do?
Yes, ma'am.
Now see, when we find the user position using angular measurements in the computation, we assume that the reference is taken at the user. Okay. Now this is all right for a camera because that is indeed the case. Reference is taken at the user. But how about this case? Here the reference to measure the bearing measurements, actually the system is designed in such a way that automatically when the user calculates the bearing measurements, it is with respect to the reference direction at the transmitter. It's actually magnetic north in case of VOR. It is magnetic north with at the transmitter. It is designed in such a way that even the user does not, if the user does not know the reference at the transmitter, the The way it is designed that when it measures bearing to the transmitter, it is automatically with respect to the reference magnetic north at the transmitter. But when he does the computation, he takes this because these reference directions are not known. So he takes the reference at the user. Now, this would not have been problematic if the earth had been a flat surface. So when the transmitters are nearby, this assumption does not introduce much error. But when the Earth's curvature introduces an error in this because of this assumption. Okay. But it is seen that this error is negligible compared to the measurement error. Okay. So in case of VOR, it is not taken into account because the order of the error, because the reference is taken at the user, is negligible compared to the measurement error. Now here you need to write the equations and find the user position when the reference direction is known. What if the reference direction is not known? What do you think you should do then? If you already know the answer, do not respond. If you do not know, think about it and then you continue. So we assume that the reference direction was known, and with that we found that two transmitters are needed to find the user position. So what if the reference direction is not known? So in this case I asked you to pick the reference direction parallel to y-axis. What if I pick some arbitrary direction? Or what if the reference is taken as north and if the direction of north is not known? What can be done? What do you think can be done? If the reference direction is not known, it means it makes some angle with this y-axis, correct? And that angle is not known. What do you think you should do in that case? So how many unknowns will you have then? How many unknowns will you have in that case? Okay, if the reference direction is known, then how many unknowns do you have? Tell me that first.
X and Y of the user,
So two unknowns, right?
two unknowns.
When there is to solve for two unknowns, you need two transmitters, correct? Two bearing measurements. Yes.
Yes, ma'am.
No,
Yes,
no
ma'am.
ambiguity. So what will you do? What will you do? when the reference direction is also not known. How many unknowns you have then? And you are? What is your name? Neela. Okay. 3 unknowns, correct? Is this clear to everyone that you have 3 unknowns? Yes or no?
Yes, ma'am.
So you have x and y coordinates of the user as 2 unknowns. To that you will get one more unknown because since the reference direction is not known, you assume that it makes some angle with the y axis and that angle is not known. So that angle is also an unknown, correct? So you have 3 unknowns, that angle which the reference direction makes with the y axis and then user coordinates, 3 unknowns. So how will you find the position? What will you do to find the position here?
Ma'am, we add another transmitter.
Yes. So we need to have one more measurement. So 3 measurements would be required to determine the user position when the reference direction is not known. Okay. Write the equations and see how you can solve for these 3 unknowns. Assume that there is no error. Okay. In the equations, you make perfect measurements of the bearings and then solve the equations to find the xy coordinates and the unknown angle of the reference direction with the y-axis. Okay. So in case of ranging, minimum 3 transmitters are required to unambiguously find the user position. In case of angular positioning, minimum 2 transmitters are needed to find the user position if the reference direction is known. If the reference direction is not known, then 3 measurements for 2D would be required. Now, is it possible to combine range and bearing? Yes, it is possible. The system is called range bearing system. So in case of range bearing system, what we do is we find the range to the transmitter as well as the bearing. Okay. So here this is shown. Bearing is calculated with respect to the north at the transmitter as per this figure, and then range to the transmitter is also calculated. Now we know that for constant bearing, the line of position is a straight line. So this is the line along which the user is located. And then the line of position for the constant range is a circle, right? And we know that a straight line intersects a circle only at one point. So the advantage of a range bearing system is that by making measurements to only one transmitter, we can find the user position in 2D. Of course, provided the reference direction is known. Okay. An example of such a system is range bearing DME VOR in case of civil aircraft. So if a base station has both DME and VOR co-located, then using measurements from only a single station, the aircraft can determine its accuracy. But since VORs are being phased out, we do not use this now. But the military aircraft can use TACAN, which is an example of a range bearing system. because they have co-located DME and BOR equivalents, okay, co-located in the same base station. So Takan is an example of range bearing system. And then another example would be laser camera. Okay, in conventional camera, we receive daylight reflected of environmental features. But if we have an active camera, say laser camera or LiDAR, the camera can transmit laser pulses, okay, and then the pulses get reflected from a feature and then returns to the camera. Then camera can calculate the round trip time. It knows when it transmitted the pulse, and then it can also note the time when it receives the reflection. So it can calculate the round trip time, just like DME. It can calculate the round trip time of the pulse, transmitted pulse from a particular feature. So this will allow the laser camera to determine the range to that feature. And then when that feature is imaged on its detector, using the same method as conventional camera, it can find bearing. Okay. So LiDAR or laser camera is an example of range bearing system. Any question? So we have seen how using bearing measurements in 2D, we can find the user position. Let's extend it to 3D now by including elevation measurements. So in 3D, we make two angular measurements, bearing and elevation. So let's define elevation first. So let's assume that the user or the receiver is located at this point. Okay. It need not be on the Earth's surface. It can be at some altitude from the Earth's surface also. Then what we do is we draw a plane tangential to the Earth's surface, but passing through the user. So wherever the user is located, at that point we draw this plane, but make it tangential to the Earth's surface. Okay, and then we also draw the line of sight to the transmitter. So by connecting the transmitter and the user with a straight line, we find the line of sight to the transmitter. Okay. Then the angle the line of sight makes with this horizontal plane, because this plane is tangential to the Earth's surface, we call it horizontal plane. The angle that the line of sight makes with this horizontal plane is elevation, denoted as theta in this video. Okay. Now let's see. So if we make two bearing measurements in 2D, we get the 2D position. Now we also want to find the height of the user because we are interested in 3D position. So let's see how with the help of elevation we can find the height of the user. So for this purpose we will consider this figure here. Okay. So we have already used bearing measurements to two transmitters to find the X and Y coordinates of the user. So the X and Y coordinates of the user are assumed to be known. Okay. Then we draw an XY plane. Okay, this is called local tangent frame because it is tangential to the Earth's surface, passing through the projection of the user on the Earth's surface. So this is the projection of the user on the Earth's surface, and we know its coordinate because we have already calculated the XY coordinates of the user. But through this point, we draw this XY plane tangential to the Earth's surface. Later we will see that the Earth's surface is modeled as an ellipsoid. Okay. For the time being, just ignore this. Some mathematical model is there. In case of Earth, ellipsoid is the most appropriate model. So we draw this plane tangential to the Earth's surface. We call this XY plane of the xy of the plane xy plane of the local tangent frame. Okay. Now then we make the elevation measurement also. How do you define elevation here? So this horizontal plane is actually this xy plane here, and we know that the line of sight to the transmitter makes this angle theta with the horizontal plane. So in this figure, this is theta. So this line is basically the line of sight, correct? And we draw this dashed line, dotted line parallel to this xy plane. So the angle that this line makes, line of sight makes, is the elevation angle of the transmitter, right? Now here we are interested in finding this distance. This is height of the user from the earth surface, right? Now as per this figure, positive z is in this direction, downward. Okay, that's why they have written minus z. So height will be negative because we assume it is positive in the downward direction. In the upward direction, it is negative. That's why they have put negative sign here. So we are interested in finding the z coordinate of the user. We have already determined the x and y coordinates using bearing measurements. And we have made the elevation angle measurement to a particular transmitter. Now transmitter coordinates will be known. Okay. If it is an environmental feature, then an additional task that the camera has to do is to associate this environmental feature with a database. Okay, so it has to identify the feature correctly. Then only from that database, the camera will be able to find the coordinates of that environmental feature. So correct association of the feature is important. Correct identification of the feature is important. That is an additional task that has to be done. In case of VOR or TACAN, the base station coordinates will be known once the aircraft receives signals. There will be some signature in the signal that will tell the aircraft which base station it is, and base station coordinates would be known a priori. Okay. So let's assume that the transmitter coordinates are known. But transmitter coordinates will be known in some other frame, need not be known in this frame, right? So let's assume in this case that this is an environmental feature and the transmitter coordinates are known with respect to some other local frame attached to some other point in the vicinity of this point. Okay. Now we also assume that the transmitter is close to the user. For example, in case of camera, this assumption holds, right? It is close to the user. If the transmitter is close to the user, we can neglect the curvature of Earth's surface. We can assume that the Earth is almost flat, and then using suitable coordinate transformation, we can transform the coordinates of the transmitter given in that other frame to this frame. Okay. So with some intermediate calculation, we can find the transmitter coordinates in this frame. Okay. Now, if the transmitter is not close to the user, if it is away from the user, then Earth's curvature will come into the picture, and if that is not taken into account, it will introduce an error in the transmitter coordinates, and that error will eventually get reflected in the user height computation. Okay. So let's ignore that now. Assume that the transmitter is close and the flat earth assumption holds. So we have found the transmitter coordinates in this frame. The transmitter coordinates are known. X, Y, Z coordinates of the transmitter are known. The only unknown here is the Z coordinate of the user. X, Y have been determined using bearing measurements. Theta is measured. So how do we relate theta to the user and transmitter coordinates? It's straightforward. Using geometry, we can write tan theta is equal to this distance divided by this distance. Right? This distance is basically the distance between the user and the transmitter in the XY plane. So you already know the XY coordinates of the transmitter and the user. So using that, we can find the straight line distance between the two, which is given in the denominator, right? So this is the transmitter, this is user. So we take the X coordinate difference square and similarly Y coordinate difference square and then sum them up. The square root of the whole thing will give you the horizontal distance or the straight line distance between the user and the transmitter. And this distance is basically the Z coordinate of the transmitter minus the Z coordinate of the user, right? So here the only unknown is this one, correct? So from this equation with rearrangement of terms, we can calculate the user height, right? So this shows how with the help of elevation we can find user height. So in 3D we require two, if you are doing angular positioning, we require two bearing measurements and one elevation to determine the user position in 3 dimensions. Any question? Anything that you could not follow? No question? Okay, let's have a 5-minute break. It's 3 past 12 now. We'll meet again at 8 past 12. Okay, so let's continue. Okay, so we have seen that in case of angular positioning, if the reference direction is known, for example, if we use north, generally we use north as the reference direction and we can determine north. using other instruments. So we can assume that the reference direction is known. So with known reference direction, we need less number of measurements to unambiguously calculate the user position. Right? In case of 2D, we require 2 bearing measurements. In case of 3D also we require 2 measurements because 2 transmitters because we make bearing measurements to 2 transmitters, and then for 1 transmitter we can make elevation measurement, and we get 3D position with the help of 2 transmitters, right? So with less number of transmitters we can find the user position unambiguously. So that's an advantage of angular position, but it has a bad disadvantage. What is that? Position error grows as the distance between the transmitter and the user increases. So let's try to understand this pictorially. Okay, so this white dot here shows the user position, and let's assume that we take the reference at the user. So this is the reference direction for bearing measurement. Now, as I told you earlier, whenever we are making some bearing measurement or any other measurements, we have some error, correct? We do not have anything called 100% accurate measurement. And that is true for this case also. We are making a measurement, so what we get is actually not the true bearing, but it is true plus some error, epsilon, right? So for this particular case, if the true bearing is psi 1, what we are measuring is basically psi 1 hat plus some epsilon. What we are measuring is psi 1 hat, which is equal to psi 1 plus epsilon. And we also know that epsilon has to be modeled statistically. We can only predict its value within some bounds, within some plus minus delta values, right? So if we incorporate the bounds in epsilon, then we can say that for a bearing measurement, basically we get a group of lines. Like the group of circles we considered in ranging, here we actually get a group of lines. So this dashed line in the middle corresponds to true bearing. And because of the bounds in epsilon, we are actually getting a number of lines around this dashed line. We are getting a group of lines. Is this clear to you? That we are getting a group of lines because we are making a measurement which has error in it.
Yes, ma'am.
Okay. Now, unlike the bands of circles, here the spread increases as the distance between the user and the transmitter grows, which is evident, right? The spread increases as we go away from the user, right? So how does it get reflected in the user position accuracy? So to understand that, let's assume that the user makes this measurement. So he, at this point, he finds that this is the bearing measurement, psi 1 hat, okay, for this transmitter. Then for this transmitter, he makes this measurement, psi 2 hat, okay. Now transmitter coordinates are known. So we know the true transmitter coordinates. And then we make these two measurements, psi 1 hat and psi 2 hat. Okay. Now, how do we find the user position using these two bearing measurements? We know the transmitter coordinates. So, to find the user position, what we exactly do? We draw a line parallel to this line, which corresponds to psi 1 hat. So, we draw a red line from the transmitter parallel to this black line, which corresponds to the bearing measurement. So this red line corresponds to the bearing measurement made by the user. We are drawing it from the transmitter because we know two transmitter coordinates. Similarly, for this transmitter also we draw the corresponding red line, correct? Now where these two red lines meet? At this point. So we determine this as the user position. The true user position is this. But using the bearing measurements, erroneous bearing measurements, we determine the user position at this point. So this much is the error, position error, right? So for these two transmitter locations, we get this much position error. Now how about other transmitter locations? Let's pick the transmitters here and here. In that case, what will happen? What do you think will happen if we pick the transmitter locations at some closer distances? Will the position error increase, user position error increase or decrease? What will happen?
Error will decrease.
Error will decrease. How about others? I am receiving response only from Apur. How about others? Ajita?
Ma'am, I think it will decrease, ma'am. I'm
It
thinking.
will.
Yeah.
You are thinking. Okay. Nilay?
Yes, ma'am. I think it will decrease.
Okay. Nikita? Is Nikita here?
Yes,
Yes.
ma'am.
Yes.
I think it will decrease too.
Okay. Shujit?
Yes, ma'am. Ma'am, no idea, ma'am.
You? What did you say?
Ma'am, no idea, ma'am. I didn't get it, ma'am.
What you did not get? What you did not get? The question or the explanation? What you did not get?
Explanation, ma'am.
Which explanation you did not understand?
The user positions, it will be decreasing or increase.
Do you understand how the user position is determined using these red lines for these transmitter locations? You understand that or not?
Yeah, from two transmitter we are getting the two position.
And this much is the
Yeah.
error that you
Users.
understand?
Yes, ma'am.
So what will happen when we pick some transmitter locations here, closer to the user? So these red lines will be closer or it will be further? What will happen? How will you draw the red lines? If, say for this transmitter, if we move this transmitter from here to here, what will happen to this red line? Will it be closer to this black line or it will be away from the black line?
Closer to this line.
So it will be closer. And how about this transmitter? If we move it closer to the user, for this also the red line will be closer, correct?
Yeah, same. Yes, ma'am.
Then what will happen to the intersection of the two lines? What will happen to that point? Will it move closer or away from this?
Closer, ma'am.
And this is the true user location,
Yes, ma'am.
right?
So it will
So
be decreased.
as you move the transmitters closer to the user, the position accuracy improves. On the other end, as you move them away from the user, position accuracy decreases, right?
Yes, yes.
So in case of angular positioning, position errors grow with the distance between the user and the transmitters. This is why we did not get good accuracy with VOR. Okay. But if we use a range bearing system, then instead of using two angular measurements, we are using one range measurement and one angular measurement. And range measurement does not have this drawback. So with the help of a range bearing system, we can improve accuracy. We can improve accuracy, and also we need less number of transmitters. So in case of 2D, just using one transmitter, we can determine the user position when we consider both range and bearing. So range bearing performance will be better, accuracy will be better than angular positioning, but it will be worse than ranging, because you are using one angular measurement and its accuracy will degrade with distance. So it will be better than angular positioning but worse than ranging. However, the advantage is that you need just one transmitter. In 2D, you require just one transmitter to find the user position. Okay? Any question?
No, ma'am.
So we have discussed ranging, we have discussed angular positioning. Now let's discuss the fourth one, pattern matching. So from the name we can guess that here we need to match some pattern. Let's see how we match the pattern, or what pattern we match. So in case of pattern matching, a database is maintained which holds some measurable parameters. Measurable parameters can be terrain height, can also be, in case of indoor positioning, the parameters could be received signal strength from multiple wireless LAN access points. Okay, we can also store environmental magnetic fields in a database. So these are some examples of measurable parameters, okay, of which we have a database. Then what we do is we measure these parameters at the current user position. So for example, if we pick one of them, say terrain height, we measure the terrain height at the current user position and then compare with the values in the database at some candidate user positions. Okay. Now, if we do not have any idea of the user position, then definitely we have to search the entire database. But if we get some prior information about the user position based on some other navigation system, then of course we can limit the search of the database. Then the best match, so we search a number of candidate points and see which position gives the best match. And that best match is taken as the estimated user position. What if we have multiple good matches? So if we have more than one good matches, or more than one good match, then we need to do some interpolation, okay, and use a weighted average of all these good matches to find the user position. Okay. So as I told you, if we have an initial guess, good initial guess from another navigation system, we just need to search part of the database. So that will limit the search of the database. But if you do not have do not have any information, then the entire database has to be searched, which is quite time consuming and computationally expensive as well. Also, the database has to be updated regularly. Okay. And the resolution of the database also matters. So it has good resolution, then it requires a large storage space, but it will improve accuracy. Poor resolution means less storage space, but degraded accuracy. Now, in case of a moving vehicle, we can measure these parameters at a number of user positions. So instead of having just one measurement, as the vehicle moves, we can measure these parameters at a number of user positions. Okay, and we can also use a date reckoning system to find the distance between these positions. In that case, what will happen is we'll have a group of measurements at a group of user positions, and all these measurements can be compared with the database to find a good match. Okay. An example of a pattern matching system is terrain referenced navigation. So how does a terrain reference navigation work? The terrain reference navigation can be used by an aircraft. Okay, the aircraft can measure its altitude above the local terrain using an instrument called radar altimeter. Okay, so radar altimeter basically sends out some radio signals. While giving an overview of GNSS, I'll define radio signals. So basically, radio signals are electromagnetic waves transmitted with frequencies within a particular range. Okay, so the radar altimeter transmits radio signals down to the terrain, and then signals get reflected from the terrain and come back to the aircraft. So by calculating the round trip time of the signal, we can find the altitude of the aircraft above the local terrain. Okay. Then using some other navigation method, for example using GNSS, the aircraft can determine its altitude above some other reference. For example, Earth's surface. Later we'll see that the Earth is modeled as an ellipsoid. Okay. When GNSS gives altitude above a reference ellipsoid. Okay, so using GNSS we can determine the altitude of the aircraft above that data, the reference ellipsoid. Okay, now in the database for pattern matching we have terrain altitudes above that data. Okay, so by subtracting the two altitudes that we got, one from GNSS, another from radar altimeter, we basically get the terrain height. And as the aircraft moves, we get multiple measurements at different locations. So we get a number of terrain heights, which we can compare with the database to find the user or the aircraft position. This method works fine when the aircraft flies over an uneven terrain, hilly terrain, mountainous terrain. But when it is flying over a water body or over a flat terrain, then this will not work. And in this case also we require information from other navigation system. Okay. But this is helpful. For example, if we use a standalone GNSS, then the accuracy may not be as good. But when if the aircraft is flying over a mountainous terrain, and if we can combine pattern matching with GNSS, we can the combined system will definitely give, provided we search the correct part of the database, will give better accuracy than the standalone system. Okay. We have come to the fifth technique, which is Doppler positioning, position fixing technique. In this case, the relative motion between the transmitter and the receiver is important. So to get user position using Doppler positioning, there has to be relative motion between the transmitter and the receiver. So let's see how that helps. So in this figure, the user is located here. Let's say RA is the user position. This is a vector quantity XYZ position. And this is where the transmitter is. Its position is RT. XYZ coordinates are represented as a vector RT. The user velocity is VA. Again, this is a vector quantity. And the transmitter velocity is VT. Okay. What is the relative velocity between the transmitter and the user? So the relative velocity of the transmitter with respect to the user would be Vt minus Va, right? And we are doing vector addition of Vt and minus Va. So this arrow here shows the relative velocity between the user and the transmitter. Vt minus Vr. So this arrow here shows Vr. Now this line is the line, straight line connecting the user and the transmitter. This is called the line of sight. Okay. So what will be the projection of this relative velocity on the line of sight? Let's say the angle is theta. This is V small r. So projection of V small r onto this line of sight will be Vr cos theta, correct? So the magnitude of that velocity is denoted as V capital R, and it is equal to V small r cos theta. And in the figure it is shown as this red arrow. So this is the projection of this velocity vector on the line of sight to the transmitter, denoted as V capital R. Now can we express Vr in terms of the user and the transmitter coordinates and these velocity vectors? Yes, it is possible. What we need to do is we need to find the unit vector along the line of sight. What is the unit vector along the line of sight? We know the RT is the position of the transmitter and RA is the position of the user. So we have RT minus RA, and that divided by the length of this line, the distance between the transmitter and the user, will give the unit vector along the line of sight. So this is the unit vector along the line of sight, right? And then we have to take the dot product between the relative velocity and that unit vector. The dot product will be V capital R, right? This is the relative velocity, Vt minus Va. And then this is the line of sight unit vector. So the dot product between the two will be again V capital R, right? Now when there is a relative motion between the transmitter and the user, when the user receives the received signal will have a Doppler shift in it. The signal is transmitted by the transmitter at some particular frequency Ft, okay, which is known. But the user would know at what frequency the signals are transmitted, Ft, okay. But because of the relative motion between the transmitter and the user, the received frequency will be shifted by a Doppler frequency, Fd, right? So the received frequency will not be the same as transmitted frequency. It will be changed depending on the relative motion between the two. Now you need to show that the Doppler frequency is given by this formula. So this is another homework problem, other than the one given in angular position. So you need to show that the Doppler frequency Fd, the Doppler shift in the received signal because of relative motion between the user and the transmitter, is given by this formula. Ft is the transmitter frequency, Vr is the projection of the relative velocity on the line of sight to the transmitter, and c is the speed of light. And then this negative sign is there. So what the receiver at the user does is, it knows the transmitter frequency, then it measures the received frequency, and the difference between the two will give Doppler frequency. It does it in the processing in the frequency domain, okay, and then it retrieves the Doppler frequency. And then since this is known, this is a known scale factor, Ft is known, C is also known. So by multiplying C by Ft and taking negative sign, it basically gets the the projection of the relative velocity on the line of sight, VR. Okay, so we can convert the measured Doppler frequency to VR and assume that VR is the measurement. In case of Doppler positioning, we assume that VR is the measurement. V capital R, which is the projection of the relative velocity between the transmitter and the receiver on the line of sight, is the measurement. Okay, we got the measured quantity. Next thing that we need to do is the determination of, since this is in 3D, we have considered 3D, we need to find the surface of position. What do you think will be the surface of position for constant VR? Assume that VA and VT are known, RA and RT are also known. RA is not known. RT is known, VT and VA are known, but RA is not known. That's why we are interested in finding the surface of position. And the measured quantity here is VR. So you are basically interested in finding the surface of position for constant VR measurements, provided RT, VT and VA are given. Think about it and then tell me what you think will be the surface of position in this case. If the question is not clear, ask me now. Do not tell me later that the question was not clear. So what do you think? It should be. Do you need more time to think about it? Or do you need some clarification? No response. At least tell me if you need any clarification.
Yes, ma'am. It's
What
not clarification.
what clarification you are looking for?
The surface of positions.
So didn't we define surface of position yesterday?
Yes, ma'am. Yesterday. Surface.
Locus of the user position in 3D for constant
Yes.
measure.
Yes,
In
ma'am.
case of 2D, it is it's called line.
Line of
In
line
3D,
of
it is
position.
surface of
Yes.
position.
Yes.
You need to find the shape of the surface for which you will get the same VR. Assuming that RT is known, both VA and VT are known. Only unknown is RA. User position is not known. That's why you are looking for a surface of position. So this requires 3D visualization. You have to see how differently you can orient theta. Theta remains the same, right? VR will be known. VT and VA are given. So V small r is known. Correct? V capital R is given. It's a constant measurement. So theta is also given, right? Now you need to see how you can orient theta in different ways so that you will get the surface of position for which you have the same VR. So what do you think? What will you do with that red line? That red arrow has to be moved in such a way that you get the surface of position. What will you do with that red arrow? When you move the user, the red arrow also moves along with it, right? So you need to move the red arrow in such a way that both V capital R and V small r are constant. How will you move that red arrow? In 3D? You need to move that red arrow in 3D. How will you do it? Keeping theta constant. So at least you can try, right? Unless you try, there's no point, okay?
Ma'am, is it a cone?
Okay, so you think it's a cone. You think,
Yes,
right?
ma'am.
How about others? What do you think? Do you agree with him? Or you do not agree? You think it will be something else? At least tell me that, whether you agree or not. And I'll come back to Apur to know why he thinks it will be a cone. So how many of you agree with Apur? Nobody. Achita, what do you think? So feel free to give your response. Okay, don't think that what will happen if I say something wrong. Nothing will happen. You are just participating in the discussion. That's it. What is the problem? If you say something wrong, say something wrong. No issue. Let's say something. At least think about it and say something. It may be right or not. But think about it. Give some explanation and say something. That's it. Yes, Ajita, you want to say something?
Ma'am, actually to keep theta constant and rotate V capital R, um, this V smaller is also interlinked with this V capital R.
V
So
smaller is given, right? Because V2
yeah,
and
it
V
is
are
given, but yeah, it is a projection. V capital is a projection of V smaller, right? So both. I mean, we
V
have to
capital.
consider V smaller also in the picture, right? So that's what I was
But that
thinking.
is
Like, how
fixed.
can we rotate both the vectors?
Why will you rotate both the vectors? Vt and Va are given, right? So they are vector
Yeah.
quantities, right? So
Yes. Yes.
V small r is also known. It's a vector quantity, so it is fixed, correct?
Yes. If
You
V
can.
smaller is fixed, then V capital R also will be fixed, right? If theta is constant.
That's why 3D comes into picture. This is not 2D. If it had been 2D, then V capital R also would have been constant. I mean, the magnitude is constant, but you have to consider the vector also, right? Vector means it has both magnitude and direction. So in 3D,
Yes.
the direction is also important. In 2D, if theta is constant, V smaller is constant, you can't do anything. V capital R also has to be constant. The direction also has to be constant. But in 3D, that is not the case. Right?
Yeah. Okay.
You have to
Got it.
pick directions in such a way that you keep the magnitude constant, keep the magnitude of both Vr and Vr and theta constant. At the same time, get some surface. So that will be the surface of position, right?
Yeah. Correct.
So what that surface should be.
Not sure, but
Hmm. But tell me, whatever you think, you tell me. See, this applies to everybody. Don't feel shy. You just tell me whatever it comes to your mind. Feel free to say that in the class.
Ma'am, are you talking about the surface made by VR vector, the capital R vector?
I'm talking about the surface of position where the user could be located. So basically, I'm looking for the locus of the user, such that V capital R is the magnitude of V capital R is constant.
Okay.
You are making a measurement, right? Measurement is a scalar
Yes.
quantity,
Yes,
right? The
ma'am.
magnitude is constant, right?
Yes, ma'am.
So you have to play with the direction. Magnitude is constant. how can you move the red arrow such that magnitude is constant, theta is constant?
Well, it's like it's supposed to be a cone, I think.
Hmm? So how will you form the cone? It will be a cone, yes, you are right. Both you and Atul were right. But how will you form the cone? Any cone will not help, right? You have to form the cone in a specific way. How will you form the cone? You have to define its vertex, correct? You also have to define the line of symmetry of the cone, right? So
Yes,
how
ma'am.
will you define them? What will be the line of symmetry of the cone? It is a conic surface, okay? Yes.
Ma'am, V small r vector.
Hmm. The
It
smaller
could be
with,
the line of symmetry.
yes. And then vertex?
RT could be the vertex.
Yes. So basically it is a conic surface, okay? The surface of position will be a conic surface. The user can locate anywhere on the curved surface of the cone, okay? And the vertex will be at the transmitter, okay? And the line of symmetry of the cone will be along V small r, the vector V small r. Now just take any point on the curved surface of the cone, you will find that theta is constant because V small r is the line of symmetry. The theta is constant anywhere on the surface, conic surface. We are not considering the base, we are just considering the conic surface. This is clear to everyone? If you do not understand, ask me, I will explain it again. Shudit, is this clear?
Yes, ma'am.
Okay. So the surface of position is a conic surface, right? For a given VR. Now, in 3D, we need a minimum of 3 conic surfaces. So we have x, y, z, 3 coordinates, right? With minimum 3 are known. So we need a minimum of 3 conic surfaces to determine the position in 3D. But how many points of intersection do we get when we consider 3 conic surfaces? Now it can be shown that 3 conic surfaces intersect at up to 8 points. Okay, so we need more measurements to resolve the ambiguity. So minimum 3 conic surfaces, 3 measurements, but since they intersect at up to 2 points, 3 conic surfaces intersect at up to 2 points, we need additional measurements to unambiguously determine the user position. Okay. Now, here we assume that the transmitter position and velocity are known. User velocity is also known. Okay. If they are not known, generally transmitter position will be known if the transmitter sends important information in the signal, then by processing that we can determine the velocity also. Okay, so we can assume that transmitter position and velocity are known. User velocity need to be found out from some other navigation system. If user velocity is not known, then we need more measurements. Okay, because they also have to be treated as unknown. Let's assume that user velocity is known, and then using Doppler measurements, or VR to multiple transmitters, we can determine the user position. So this is the measurement. Ignore this arrow here. This is a scalar term. Okay, we are taking dot product. So this is a scalar term. So ignore this arrow on top. So we are finding this one from the Doppler shift using that formula you are supposed to derive. So from the Doppler shift we find V capital R, and then here if we assume that Vt, Rt and Va are known, only unknown here is Ra. Okay, so we need multiple measurements. Even when only Ra is unknown, we need multiple measurements to determine Ra. Alternatively, if we do not get multiple measurements simultaneously from different transmitters, what you can do is we can get measurements from the same transmitter over a period of time. If the vehicle is stationary, user is stationary, not moving, then for all these measurements, RA remains constant. But what if the user is moving? If the user is moving, then RA is also changing, right? In that case, what we can do is we can use some dead reckoning system, okay, and find the change in position. So here we see the relationship between the initial user position and the user position at some time instant, other time instant, and this is the change in position. So we can use a dead reckoning system to determine the change in position. Okay, then in all the measurements that we stack over a period of time, only unknown will be the initial position. By solving the measurements over a period of time, we can get the initial position. Okay. The examples of Doppler positioning are transit and iridium positioning. Transit was developed before GPS. Okay. By the Applied Physics Laboratory at the Johns Hopkins University. It was a constellation of 4 to 7 satellites at low altitude orbits. Orbital radius was of the order of 1100 kilometers. At a time, only one satellite was visible to the user. Okay, and the time between two successive passes of the same satellite was about 100 minutes. So the user had to wait for 100 minutes to see the same satellite again. And once the satellite was visible, the user could get measurements, Doppler shift measurements from the satellite for about 10 to 20 minutes. Okay. Now, with the help of transit, 2D positioning accuracy of about 25 meters could be obtained. Okay, and transit was used by US submarines. Okay, so they used transit to determine 2D position and also to correct INS error. So submarines will come to the surface uh, uh, at some regular intervals to correct for few different things. So one of the requirements would be to correct the INS, inertial navigation system. So they use highest quality navigation, inertial navigation system called navigation grade INS. But still the system drifts over time. Okay, the error grows over time. So periodically it has to come to the surface of the water to correct for the errors. So they use transit signals to correct for INS errors also. Transit is no longer operational. After transit, GNSS was developed. GNSS is used now. Another example of Doppler positioning is iridium positioning. So this is basically a satellite communication system. So you probably have heard of satellite phones, where long distance calls are made with the help of satellites. Okay. Iridium constellation is used to make long distance phone calls through satellites. It's a satellite communication system basically. It has 66 satellites again in low altitude orbits. Orbital radius is about 7,600 kilometers. Okay. So using Iridium also it is possible to find the user position. Um, so about 30 to 100 meters 3D positioning accuracy can be obtained using an Iridium satellite in 30 seconds. Okay. So using just one satellite over a period of 30 seconds, so we can get 30 to 100 meters position accuracy, 3D position accuracy. Here from the same transmitter we are stacking measurements over 30 seconds, and by processing them we can get 30 to 100 meters accuracy. Recently, there is a trend of launching small satellites in low Earth orbit, low altitude orbits. SpaceX, Elon Musk's SpaceX launched many small satellites recently. Two of the satellites were about to collide with the Chinese space station. So China complained about this in the United Nations. Now that many low Earth orbit satellites, small satellites are being launched, people have started exploring this Doppler positioning method with the help of these low Earth orbit satellites, LEO satellites. Recently, I saw a paper by an eminent researcher where he did detailed simulation and analysis to show the accuracy that could be obtained with such a system. Of course, he considered many satellites, some 20 to 30 satellites, but he showed that it is possible by if the satellites transmit suitable signals, it is possible to obtain meter level accuracy. 5 to 6 meters accuracy can be obtained with the help of that operation. Okay, so with this we have completed all the navigation techniques. I just want to make one more comment. Now while discussing all these techniques, I think you have got the idea that a good strategy is to combine different methods that complement one another. A good example of such integrated system is integrated GNSS and INS because they complement each other. INS error grows with time, whereas GNSS error does not. So whenever GNSS signals are available, we can calibrate INS error so that the INS can breach through the GNSS outage period. I've also shared a link to a presentation where you will get to know about novel application of integrated GNSS INS system, how they navigate an aircraft through a hurricane using GNSS INS. And the presenter said that they get reasonably good accuracy. So within the hurricane, GNSS signals will not be available. At that time, they use INS for positioning. There are different levels of integration architectures. So as complexity grows, we get better accuracy and robustness, but at the same time, computational load increases. Now, GNSS INS integration is not the only example. We can also integrate GNSS with camera and INS. GNSS barometric altimeter, which gives altitude, INS camera, they all can be integrated. Uh, uh, so the integrated navigation system basically aims to eliminate the disadvantages of individual systems and retain the advantages of them. Okay. So that's it for today. In the next class, I'll first give you a brief overview of GNSS so that you can get started with the project. And then we'll talk about different navigation coordinates. Okay, any question? You are okay with the pace? Am I going too fast?
No, ma'am, the pace is fine.
Okay. That's it. So we'll meet on Wednesday again.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.